Now that we've talked about stress-strain diagrams and this relationship between stress and strain, there's one more relationship we should talk about, which is a relationship between strain and strain. And this is a relationship called Poisson's ratio. Poisson is some French guy who came up with this ratio. Yes, it is the French word for fish, but it's not named after the fish, it's named after the man. So this is Poisson's ratio, and it is the ratio of the lateral strain that we see in a body to the longitudinal strain. So what that looks like, Poisson's ratio as an equation is the Greek letter nu, which looks kind of like a fancy V is the way that I draw it, but it's the Greek letter nu. And that is the negative lateral strain over the longitudinal strain. And when I say latitude and longitudinal strain, what that means is that when we take our specimen, like we do with our Play-Doh, we take whatever our specimen was, and we stretched it out, we applied some force to it, we get a new shaped specimen, right? So when you roll out a snake of Play-Doh and then you pull on it, you notice that it goes both outwards and gets skinnier, right? So our shape changes from this original white square to this dashed line here as we're stretching it out, as we're applying that load to it. So when we apply that load, we notice that the direction that we're stretching it out in had this original length of L, and then it expands on both sides. Right, so this is in the longitudinal direction. Longitudinal direction. It's in the same direction as the direction we're pulling, the normal force, if you will. The longitudinal one, it's getting longer. And this would be delta over 2 since it's on each side. Right, so here's a delta over 2. Where our lateral strain would be delta over L, right? And it stretches so that on each side it gets some additional material over what the original length was, assuming it moves in both directions out from the center here. And then our lateral is the one moving inward and outward from the side here. So we can think of it as like if this were maybe a pipe or something like that, and it has some initial radius R, or the full diameter D you could use, but I'll use R since we'll have a lot of D's in here. So some radius R of the pipe, which then gets skinnier as we're pulling it. It's getting skinnier, so it's actually losing this distance here, which is why we have the negative sign in this equation, because we want the Poisson ratio to come out to be a positive. So this is a negative because this displacement goes inwards. And we're going to call this, I'm going to call it just delta prime. It's just the lateral displacement. So see, and I already wrote these backwards. This is longitudinal, and the lateral one, that's our radius one, perpendicular to the direction of the force that is stretching this out. So delta prime over the original radius R. And again, this lateral one usually comes out as a negative, so we put in a negative to negate it. We want it to come out as a positive. The Poisson ratio, much like modulus of elasticity, is something that is known for a given material. So it's a constant that you can look up in the tables just like we can for modulus of elasticity. And we're going to find that for most materials, well, for all materials, it's going to be between 0 and 0.5. 0.5 is the absolute maximum a Poisson ratio can be. But most of the time, usually when you look these up in the charts, they're somewhere in the 0.25 to 0.3 range. That's a typical range for the Poisson ratio, but can be anywhere between 0 and 0.5. It is dimensionless, so it's just a ratio, right? It's the same thing over the same type of thing over another type of thing, strain over strain. You get a dimensionless quantity that does go with the material. So we can use this in a few ways with our stress strain diagram and our properties of specific materials to calculate things like stress and strain. So let's look at an example of how we might use this. So in this example, we have a small cylinder of 2014 T6 aluminum that's placed in a vise with an 800-pound force axially loaded on that cylinder. It has a length of 1.5 inches and a diameter of 0.5 inches, and we want to find the decrease in length and the new diameter of this little rod under this applied stress. So the very first thing I'm actually going to do is I'm going to look up this material in my tables and see what known information I can get. Again, that Poisson ratio is a known ratio. So if I look in my table that we have in the back of our book, I'm looking for, it's the very first one on our table here, aluminum 2014 T6. And I'm in the customary units since I was in inches and everything. And I'm just going to write down these values, anything that I see that might be useful. So I'm going to grab the modulus of elasticity, which is 10.6 times 10 to the third KSI. I might as well grab the yield strength while I'm here. It's 60 KSI in compression and tension. So this one is in compression. We know it's being squeezed in. So since it's the same, it doesn't matter, but it is the 60 in compression. Ultimate strength is 68 in compression. And then the Poisson ratio is given on this right end of the table. It is 0.35. So I'm going to grab those numbers and just pop them in here for my own reference. So the modulus of elasticity from the table was 10,600 KSI. The yield stress was 60 KSI. Ultimate was 68. And the Poisson ratio was 0.35. So that's all just from the table, just so I know that I have some numbers I can start with, right? So we want to find the decrease in length and the new diameter. So we know that we can use strain to find these changes in length, right? Those strain equations that we have. So if I want to find the decrease in length here, my change, decrease in length, is going to be that relationship between the strain, the longitudinal strain, and the overall length. So I know what the overall length is. It gave it to me, this 1.5 inches, but I don't know what the longitudinal strain is. So what I'm going to have to do is find the strain. And I know the loading and the cross-sectional area. So I can calculate stress if I want to, and I also know modulus of elasticity, which relates my stress and strain. If I write this out, since I know that my strain by Hooke's law is related to stress by normal stress over modulus of elasticity, I have modulus of elasticity, and my normal stress is the load over the area. Again, I have both of those, so I can calculate everything basically back through these equations. So if I calculate my stress, then I can get my strain, then I can come back here and get that displacement. So all of these different aspects that we've learned in our stress-strain diagrams, these relationships, will help us backtrack through, relate things to each other, even if they don't quite seem related at first. So I can calculate this stress. This is 800. Actually, since all of my units in here are in KSI, I'm actually going to convert this to kips. So 1 kip is 1,000 pounds. So this is 0.8 kips. 800 pounds is 0.8 kips. Over the area is pi over 4 times d squared. D is 0.5. Sorry, 0.5 inches squared. So pi over 4 times 0.5 inches squared. And that gives me a value of 4.07 KSI. Now, when we calculate this stress, we need to note whether we're in tension or compression with our sign convention. So since we're in compression, this is actually going to be a negative stress that it's experiencing. Negative means compression, positive means it's in tension. So since it's being squished in, we're going to call this a negative. And this will be important because it carries through back these other calculations, and we're calculating a decrease in length. So we should see a negative number for a decrease in length. So this negative will carry back through. When I plug into this strain equation here, I have negative 4.07 KSI over the modulus of elasticity we got from the table, 10,600 KSI. And when I pop that into my calculator, it gives me a strain of, again, negative, which I didn't leave room for, but negative 0.0000384. And this is technically dimensionless, but I'm going to put inches per inch for my strain here. And then to get my decrease in length, my D here, I'm just going to multiply my strain by the overall length. If I multiply this by the 1.5 inch length, then I get delta D. Delta is negative 0.000577 inches, which is, not a lot, but it is something. There is a change there. It's a very, very, very small change, imperceptible to our eye, but there is a change there. So the decrease in length is this 0.00057 inches. So that was the first part of the question. The second part asks for the new diameter. So the new diameter, we can go through a similar process, but now that we have the longitudinal strain, we can use that with our Poisson ratio to find the lateral strain. Because we know the Poisson ratio is negative strain lat over strain long. So if we want to find strain lat to get what that new diameter is, right? Since we have d prime is the strain epsilon lat times the radius, we can go through, we have the Poisson ratio. This is 0.35. We just found this, the negative 0.000384. So we can plug those in. If we multiply those together, I get strain lat is now a positive, because if we think about it, when we're squishing it, the diameter is actually getting fatter and fatter. Just like when you squish down a little Play-Doh snake, he gets fatter and fatter as you squish him down. This is the same thing. He's going to be getting fatter, so now this strain is a positive number. And I get 0.001345 inches per inch. And now I know my original radius here, or diameter. You can use either. So I want to get the new diameter. So I'm just going to use the diameter. If I do this times 0.5, then I'm going to get the increase in length there is 0.0005 0.067 inches. Now again, it asks for the new diameter. This is just the increase in the diameter. So what I want to do is add the old diameter to this number, right? Do the plus 0.5 inches to get the new diameter. So don't skip that step. Don't stop here at what the increase is. It asks for the new diameter, so it's 0.50067 inches. So it saved us a few steps in having to go through the whole Hooke's law calculation with modulus of elasticity and stress. Instead, we could just use the Poisson ratio and the definition of strain here to get the new diameter a little bit more quickly.